Hey there. Let's talk about one-dimensional kinematics. Kinematics is the science of how things move. We'll explore the general case, and then the case for constant acceleration, and in constant acceleration we'll look at the case of free fall. Here I've just taken some function of position versus time, took the time derivative of that function to get velocity versus time, and then I took the velocity versus time derivative to get acceleration versus time. What you can see here is that where there are zeros in the velocity versus time function, there are minima or maxima in the position versus time function. Similarly, where there are zeros in the acceleration versus time function, there are minima or maxima in the velocity versus time function. So you can see that the slope of the position versus time graph is the value of the velocity versus time graph, and the slope of the velocity versus time graph is the value of the acceleration versus time graph. We can also see that the inverse is true as well. So the area under the curve of the velocity versus time graph is the value of the position versus time, and the area under the curve of the acceleration versus time gives you the velocity at that time. For constant acceleration, we can take the integral of the acceleration, and it's a simple function. So if a equals constant, when we take the integral of that, we get the velocity function from t0 to t final. That just gives us the acceleration times time plus the constant v0. When we take and substitute that velocity function into the integral for the position function, we come up with our kinematic equation, 1/2 at squared plus v0t plus x0 equals x final. Let's look at what this position function means in some detail. So x final, that means if I started at some place x0, that's where I end up at x final. So this x0 part is the displacement of where I started away from the origin. And oftentimes we just set the origin equal to x0, but sometimes in a problem with several parts we don't do that. We have it wherever we started at that particular part of the problem. The second term, v0t, that's the displacement involved with the motion of the particle, or me. So I have some initial velocity, I'm moving for some time t, that gives me a displacement. I add to that the third part, the 1/2 at squared, that is a displacement as well. That is accounted for by the fact that I'm slowing down or I'm speeding up. So where I end up involves all three of those, where I started, the fact that I was moving, and then also the fact that I was slowing down or speeding up. Now let's do a practice problem. We'll throw a rock upward with initial speed v0 from initial height y0. We want to answer three questions. When does it reach its highest point? What time? How high does it go? When does it land? I'm going to start by drawing a simple diagram. Just a stick person here throwing a rock upward. Oh, I'm really only doing 1D kinematics, but it's a little hard to show one line going straight up and straight down, so I've expanded it just a bit. I'm going to label things on the diagram that matter. So the y0, that's where it started, and it started with an initial speed v0. I'll call y1 to be the maximum height of the object, and then y final where it lands back down on the ground. Next thing I want to do is draw some position versus time, velocity versus time, and acceleration versus time graphs. And so you can see that if you start with the acceleration versus time graph, that's the simplest one to do. I have constant acceleration, which is -g. That means my object is changing its velocity with respect to time all the time at the same rate, and that rate is -g. Now, since I started with an initial velocity, my velocity versus time graph has some positive v0. I've thrown the rock upward, and then it goes up to stop at the very top. That's where my velocity goes to 0. I'll call that t1. And then it continues down, and you can see that the velocity becomes negative and gets larger and larger in the negative. My position plot, it starts at some positive y0. it is parabolic. We expect a quadratic function because we have a linear velocity versus time plot, or a straight line graph. Has y1 at the top of the trajectory. That happens at t1, and then there's a parabolic curve coming back down. Now this plot I've drawn a little past where y equals 0. If you were throwing a rock over a cliff, it could continue down. For this problem here, it would stop when it hit the ground, which would be y equals 0. Okay, now I've got my diagram and my kinematic graphs. Now I'm going to start doing some math. Write down what I know. I know V0, I know Y0. What I want is T1 here. We'll start by working on when does it reach its highest point. I'm going to write down the general kinematic equations that we derived a few minutes ago. Y final equals Y0 plus V0t plus a half AT squared, and V final equals V0 plus AT. Now I'm going to specify the equation, the velocity function, just for this problem. So my y final at the very top, that goes to 0. My v0 is just v0, and then my acceleration is minus g, and the time I've specified that to be t1. Now all that's left to do is to solve for t1. Simply, t1 equals v0 over g. Okay, now let's work on the second question. How high does it go? I'm going to start by specifying my position function for this particular case of the problem. So my y final here is y1, my y0 is still y0, v0 t1, because I'm talking about t1, and then the acceleration is negative g, so I have a minus a half g t1 squared. So now what I can do is I've already found out what T1 must be in terms of the given variables, so I can substitute in T1 into the two different places where I see T1 showing up in the equation. I can do a little bit of simplification, multiply the V0 through and cancel one of the powers of G, and what I can do is combine those two last terms into one term. This just gives y1 equals y0 plus 1/2 v0 squared over g. That's how high it goes, depending on initial variables. So notice it's all in terms of the given variables. Now let's work on the last question, when does it land? I start by specifying the general equation to my specific case. I can see that it lands at 0, so I set y final equal to 0. I still have y0. My v0 is the same. My t final now is the t when it actually lands, and minus 1/2 gt squared for t final. I can see that this is a quadratic function, so I'm going to put it into the form t final equals negative b plus or minus b squared minus 4ac all over 2a for the generalized equation for the quadratic function. My b term is v0, so negative v0 plus or minus root v0 squared minus 4ac would be minus 4 times negative 1/2 g times y0 all over 2a turns into 2 minus negative 1/2 g. I can do some simplification here. I can multiply through the negative sign and simplify the last term under the quadratic. And also then I have to think about choosing the correct plus or minus term for the root function. Now I notice that the term under the square root, v0 squared plus 2gy0, that's greater than v0. If I take the square root of that, I have v0 squared adding something to it, so I should have some larger value, and I can't take and subtract a larger value than v0 from v0. I'd have a negative time. It actually would give the intercept before I actually threw up the rock. So I know I need to choose the positive sign here. So in conclusion, we talked about the general case. We saw that velocity is a time derivative of position and acceleration is a time derivative of velocity. In the inverse, velocity is the integral of acceleration and position is the integral of velocity. We did a derivation of the kinematic equations. For constant acceleration, we find that v final equals v0 plus at, x final equals x0 plus v0t plus a half ad squared. And be careful, only use these when you have constant acceleration. For a problem with free fall, the acceleration goes to minus g. And then we did an example problem where we would have acceleration negative g in a free fall problem. Thank you for coming. Come again soon.